All right, let's look at another example where I'm going to calculate both standard deviation and the relative percent standard deviation. I have 3 trials worth of density data, 11.44 grams per milliliter is trial 1, 11.38 is trial 2, and 11.30 is trial 3. So here's my 2 equations I need. There's the standard deviation equation, and now the percent relative standard deviation is simply the standard deviation divided by the average times 100%. Okay, let's start with the standard deviation first. So what I need is my average. The average of that data is 11.373333, but I need to round that to represent the 4 significant figures that I have in my data, precise to hundredths place. So rounded, my average is 11.37 for significant figures, and that's the average that I'm going to use in my standard deviation calculation. So let's carry that forward. I have 3 values of y, my 3 trials. There's my y bar, is 11.37, and then n, number of samples, is 3 this time. So let's write out the standard deviation equation. So here, S is going to be the square root of my 11.44 minus 11.37 squared, the 11.38 minus the 11.37 squared, and plus the 11.30 minus 11.37 squared. All of that is over 3 minus 1. In this case, my n is equal to 3. So let's take a look at where each one of those comes from. So I have the 11.44, which came from trial 1, 11.38 from trial 2, 11.30 came from trial 3, and of course the 11.37, which appears in every term, is my average. Okay, so let's evaluate each of those expressions in the numerator and the denominator. So that becomes square root of 0.07 squared plus 0.01 squared plus a negative 0.07 squared, all of that over 2. So I'll just go ahead and evaluate all of that through, and I end up with the square root of 0.00495. So let's go ahead and evaluate that square root. That'll be my final value of S. To the number of digits that I have in my calculator, that's 0.07035624. The units for standard deviation will be the same as the units of my starting info, grams per milliliter. Now I have to realize that I have way too many digits of precision in that standard deviation. I need to round it. So how will I do that? What's limiting my number of significant figures? Let's take a look at these equations in parens in the top here. So if I look at each one of these subtractions in parentheses, what I end up with is each one of them having only one significant figure. So what that means is my standard deviation can only have one significant figure too. I need to cut that off after 1 sig fig. So I'll stop at the 0.07, round there, and my final answer for standard deviation has just one significant figure. Now again, that's going to happen a lot, even though my data has 4 sig figs, because subtraction is oftentimes resulting in a loss of significant figures. I end up going from 4 down to only 1 remaining. All right, the only thing left then is to calculate the percent relative standard deviation. I'll take my standard deviation, and again, I'm not going to use the rounded part. I'm going to go ahead and keep all the digits until I get to the end. So I'll have the 0.0703564, and I'll divide that by my average, the 11.37. That average is the same as in my data, multiplied by 100%. When I do that, I get 0.618788%, and again, I need to round that to one significant figure, so my relative standard deviation is 0.6%. Okay, let's do the percent error calculation for this same data set. I have my same 3 trials with the same average. Then I'll need to know the actual value to calculate the percent error. This set of measurements of density is for a sample of lead. The actual density of lead is 11.34 grams per milliliter. Let's then get my percent error formula. Percent error is the absolute value of the average minus the actual divided by the actual times 100%. So let's plug in. My average value is 11.37 grams per milliliter. Subtract from that 11.34 grams per milliliter, absolute value of all of that, and then divide by the actual, which is 11.34 grams per milliliter times 100%. Okay, a quick evaluation of the numerator, 11.37 minus 11.34, so 0.03. I would then divide that by 1134, multiply by 100%, and this is what my calculator gives me. Now clearly that's way more digits of precision than my actual data, so I need to round this answer. So again, how would I do that? Well, let's look at where my significant figures are limited. The limitation in significant figures comes from right here, from this numerator. If I look at this, I see that when I do the subtraction, I can keep out to hundreds place. Once I do that, the 0.03 is only one significant figure, meaning I need to round this to 1 sig fig. So my final percent error is 0.3%, accurate to 1 sig fig.